right, hello everybody. Welcome back to EAS205. So did you get your robots working for the homework mostly? Yeah, right. That's good. I realized that the Monday to Monday cycle probably was not the best idea because lots of people ended up struggling with it at the last moment, and during the weekend was difficult to get some help, you know. So I think we will switch, as you noticed, I didn't post any homework now because I think we will switch to Wednesday cycle instead. And sometimes maybe it won't even be that regular. Sometimes it'll be like midterm stuff, so we will do like midterm practice problems instead, and so on. So it will be more like let's play it by ear, whatever is convenient. So I think the next homework, which will be on this topic, on solving systems of linear equations, I think I will post it on Wednesday. Also because I need to first explain the theory, what can all go wrong with solving systems of linear equations. And then let you do homework so you can actually check what can all go wrong for yourselves. I guess that's really how you learn it, right? That's how you learn the coordinate transformations on the robot, but like making mistakes and realizing, aha, wait a second, this actually does matter. Okay? So solving systems of linear equations is something incredibly important. That doesn't occur just like in graphics and physics-based animation, but pretty much everywhere in engineering. You know that MATLAB does it for you. You probably know that, right? This is the MATLAB / operator. But what I'll be talking about is essentially the basic system, the basic ideas for how it works, and most importantly, what all can go wrong. Another motivation is recently watching the convex optimization lectures that are online. By the way, they sort of inspired me to do lectures like this, to print it out and then annotate it here because they are really well done. And what the professor explained, what the professor emphasizes that like every lecture, like 2 or 3 times, he says, if you are smart about your linear algebra, if you can solve systems of linear equations efficiently, then you know how to write these convex solvers efficiently. So this if is essentially what we will be talking about. So this is a basic building block of then a nonlinear solvers, of convex optimization solvers. If you heard about linear programming, quadratic programming, that's what I'm talking about. And how these things work, and other optimization things too, like inverse kinematics and so on. Or in physics, integrating Newton's equations of motion. That's what we do at physics-based animation. All these things, no matter how fancy math, they boil down to some systems of linear equations you have to be solving over and over again, typically iteratively. That's why it's so important to have efficient solver of linear equations. So we'll not really get there to like how to optimize the solver, those are advanced topics, but we're gonna cover the basics. All right. So we'll start with something that's really dumb, just to give you an idea that some of these issues actually appear already in the really dumb 1-by-1 case. So I guess, so we start with a 1-by-1 system, which is still a valid system of linear equations, because the interesting thing is that you can see the problem cases already there. It's just that in matrices they will be a little bit more concealed, so I think it's good to start with this. So I guess you can think about it as unmultiplication. So we have like an equation, it's really dumb, just one unknown, that's the x, right? And we have to solve for how much the x is. So basically, what do we need to multiply 5 with? So we get 10. That's why on multiplication, right? And here it's really dumb. It's like, I guess, I don't know, kindergarten type of problem, right? So you know, of course it's 2. So what all can go wrong with such a simple thing as just like a single linear? Actually, I should probably say affine equation. Well, here is one thing that can go wrong, right? If for some reason somebody asks me 0x is 0, that it turns out that anything really is a valid solution, right? 1, 2, minus 10, whatever multiplied by 0 gives me 0. So in this case, there is infinitely many solutions, right? And that's perfectly fine. That's what this equation wants, right? And even more interesting case is if the right-hand side is not 0, in this case, there is no solutions, right? Because if we want 0x equals 5, no matter what we can multiply with whatever we want, we'll never get the 5, right? We'll always get 0. So in this case, no solutions, okay? So already in this dumb case of 1-by-1 system, we see that there are actually 3 cases we need to distinguish. And in this 1-by-1 system, it's like really simple, right? You just, well, let's look at it. So there are 3 cases. Either there is a unique solution, there is infinitely many solutions, or there is 0 solutions. Okay? And how do you detect? So how do you detect them? Well, the weird case is if there is 0, right? And in that case, there will be either infinitely many or no solutions, and that depends on the right-hand side, right? If the right-hand side is good, means we'll have infinitely many. If the right-hand side is bad, we will have no solution. All right? And why I'm bothering you with such a dumb example is that the same situation will occur with matrix equations, with systems of linear equations, except that it won't be so easy to see that. Here it's like really staring at you. You're like, what are you talking about? 0, right? What do you want to do about it? Well, in the matrix, you won't be able to see that clearly. In the matrix, it will be sort of hidden, this fact that it's one of these cases. And unless you do some more advanced linear algebra, it's not easy to discover. So keep this in mind when I'll be talking about singular matrices and so on. This is a good way to remember it, just 1-by-1 system on multiplication. All right, let's do some real system of linear equations, which is not completely dumb and not very complicated. But so at some point, I believe you all know how to solve a system like this. So what I have to do here, I have 3 unknowns, x, y, z, which are real numbers. And I need to find such x, y, z such that all these 3 equations are simultaneously satisfied, right? You can be giving it also to geometric interpretations. I think that's elaborated on in the book, that you can like look at it as like intersections of hyperplanes or whatever you want. But ultimately, all you need to do is just find x, y, and z such that all these 3 equations are satisfied. I guess that's the algebraic point of view, right? So how do you do that? One answer I will accept. You will type it in MATLAB. Another answer. Yep.
Leave one unknown on one side of each of these one of those equations, and then move the other unknown on the other side, and then substitute into some other equation.
So I couldn't hear you properly, but I believe what you are referring to is basically the process that's known as Gaussian elimination. Basically, do linear combinations of these equations to reduce it to a triangular form where you can apply a back substitution. So that's exactly, let's work through it actually, because what I want to get to is then a matrix form of this. So let's first work through the basic Gaussian elimination. I think that's what you were alluding to. So we start, so what we'll be doing, we'll be rewriting the system of 3 linear equations to an equivalent system which has the same solution by doing simple operations. These simple operations, I guess they are called row transformations. Is this? Oh, sorry, it's not this sharp. It's not something form. That's much better, right? Please yell at me if there is something not nicely visible. So what we do, what we do in the first step is that we take the first equation, multiply it by -2, and add it to the second equation. Okay. So what we get is we do -2 times the first equation. So let's see. So we are working on this one. So we take the first equation, multiply by -2. So that gives me -4 plus 4, that gets 0. That was actually the point. That's why I multiply by -2 so that the first element disappears. -8 plus 9 is 1. There will be that will be 4, -3 is 1. And the same thing goes for the right hand side, so that would be -8 plus, -4 plus 8 is 4. Okay, so that's right. And we do the same thing for the second equation. So here I have to multiply the top equation by 1 and add it to the third one. So multiply the first by 1 and add it to the third one. So here the x disappears, that's the point, right? And here if I do 4 minus 3, I get 1. -2 plus 7 is 5, and 2 plus 10 is 12, okay? So that was one step of Gaussian elimination. And so let me just carry over the system. This is the system which we ended with. And we do one more step. I'm sure you all have seen this, right? Anyone who hasn't seen this? Good, good, good. So the final step, basically, now we have brought it to this form, so now we can forget about the first equation. And what we do, we take this equation, multiply by -1, and add it to the last one. So what we get by doing this, we get 0 here, we get -1 plus 5 is 4, and -4 plus 12 is 8. So we brought the system to an equivalent, we transformed it to an equivalent system, right? Just like when you are doing transformations to a single equation, you know that they are equivalent. And the point is that now this can be solved quite easily. So what we did, we transformed it to this form, and here what we can do is called back substitution. Here it's easy, right? Because we see from here you can immediately see that z must be 2, right? If we know z, we can substitute it in here. So that means I get 1i plus 1z. If z is 2, that means that y plus 2 is 4. That means that y must be 2, right? 4 minus 2. And now I know what is z and y, so just plug it in into the first equation. So I get, let's see if it adds up. It's always good to check it, you never know. 4 times 2 minus 2 times 2. So this would be 2x plus 8 minus 4, that's plus 4 equals 2. So I get 2x equals minus 2. So indeed x is minus 1. So this process is called back substitution. Okay. So the triangular, this is sometimes called triangular system because it has like this triangle form. I'll have more to say about that later. So the simplified system is easy to solve because it's triangular. So that means you can really apply this back substitution. You can probably see that doesn't only apply to 3 by 3 matrices. If it was a 100 by 100 matrix, it would work exactly the same way, right? You just work your way up, substituting the variables you have already computed. Okay, so that's clear, right? Okay, so let's now put it into matrix perspective. That's where it starts getting more linear algebraic or matrixy, because we have all this nice theory of matrices, and we know about matrix vector multiplication, and the process of Gaussian elimination can be phrased beautifully in the language of matrices. So let's take a look at that. So first of all, which is sort of obvious, I can just write a system of equations as matrix vector multiplication equals some right-hand side. So the matrix is known, those are the coefficients of the system of my linear equations, and the right-hand side, those are just the values on the right-hand sides of the individual equations, right? Easy breezy, right? And you must remember how the matrix multiplication works. If I multiply this, it's exactly what was happening in the linear equation. So you can see this is basically nothing but taking inner product of each of the row and multiplying with the vector of the unknowns. Okay. The point of this is that now the cool thing is that we can express the Gaussian elimination as matrix multiplication. And matrix multiplication with some special type of matrices, in particular this type of matrices. So if you remember, what did we do to the system to actually bring it up? So what was the first thing when we were solving the system? What was the first thing we did? We took the first equation, multiplied it by -2, and added it to the second equation. Okay. So how can we do this with matrices? Well, we can define this special matrix, 1, 0, 0, -2, 1, 0, 0, 0, 1. This is called like elementary row transformation, I guess, something like this. And this matrix has the property that if I multiply it with arbitrary matrix, what it does is exactly what I want. It takes the first row, multiplies it by -2, by this -2, and adds it to the second row. And the first and the third row, they are intact. I guess the one way you can look at it is like this. So we had matrix multiplication before, right? So you know that if I have a matrix A, apply to vectors, I don't know, b1 to bn, then the result is ab1 up to abn, right? I can also look at it other way. If I'm multiplying from the left with some, if I write the rows of another matrix C, oops, this was supposed to be, okay, I'll do it again. C1 to Cn, those are some rows. So those are like row vectors this time. And I'm multiplying with A. What do you think we will get? Well, now these are row vectors, so I get C1A up to Cna. Okay. So those are basically two equivalent ways how you can be looking at matrix multiplication. When we will talk about transposition, it will be completely obvious that this is the case, at least for symmetric matrices. But that's basically what's happening here, right? This is matrix multiplication, so I can be looking at it this way. So I'm applying one row, multiplying one row at a time. So this row gets multiplied by the entire matrix. Well, if this row gets multiplied by the entire matrix, what does it do? It just copies the first row, right? Everybody sees that? Everybody has a mental picture of matrix multiplication. If this row gets multiplied by this matrix, then that's when the interesting stuff happens, right? I get the first row multiplied by -2, and I add it to 1 times the second row. So that's the elimination operation. That's what I want. That's what creates this, right? Because I do -4 plus 4 is 0. That's why I'm doing it. -8 plus 9 is 1. And 4 minus 3 is 1. Okay? And then the last row, well, what does it do? Again, it just copies the third row of the matrix. Right? Everybody got it? Now the important thing, I do the same thing on the right-hand side too. So basically, this is actually why it's equivalent, right? Why this is an equivalent problem, because I apply the same matrix, and in a little bit we will explain that this matrix actually is invertible. So that's why it is an equivalent problem, and apply it both on the left-hand side and on the right-hand side. So this is the same matrix. This is the elementary row operation. I guess it's written here, right? So here I just apply to the vector. By the way, in some cases you might be solving a system with multiple right-hand sides. So if you have multiple right-hand sides, you could just have a matrix of multiple right-hand sides. That would be totally fine. And if I do that again, the same idea, right? The 1 multiplies 2, so that just copies the 2 here. -2, that does -2 times this plus 1 times this, so it's -4 plus 8, that's 4. And this just copies the 10 over here. Okay? So this is exactly the state of the system after the first operation of Gaussian elimination. And the nice thing is that here I was able to express it purely using matrix multiplication, using a specially defined matrix. This matrix is going to be important in the following that's coming. That's LU decomposition. And this is essentially how we get to it. Well, let's look at how do we proceed. So after this multiplication, we got this matrix form, right? So now I take this matrix and copy it over here. So this is the matrix I ended with in the previous step. And here I do another operation of Gaussian elimination. So this time the matrix, now try to observe the pattern of these special matrices, which basically encode the Gaussian elimination process. So this one, what does this matrix do? It lets the first row through, it lets the second row through, and this adds the first and the third rows. Okay? Everybody sees that? Same thing goes on the right-hand side, right? So I guess if we do it here, so first gets copied, second gets copied, and the last one is just the sum of the first two. So 2 minus 2 is 0, 4 minus 3 is 1, minus 2 plus 7 is 5. Same thing goes on the right-hand side. The first value gets copied, second value gets copied, and the last value, that's 2 plus 10, that's 12. So the sum of the first and the third one, okay? I'm doing the same Gaussian elimination as I showed you before in the system of equations, but this time I'm doing it by multiplying by specially formed matrices, by the elementary row operation matrices. Yeah. So here is the last step of Gaussian elimination on this example. The last step, look again, the key is this matrix, right, which is applied. This is the same matrix applied both on the left hand side and on the right hand side. So this thing, again, lets through the first row, lets through the second row, and what happens to the third row? It's the sum of the second row and the third row, minus 1. So sorry. So the second row minus 1 plus the third row. Okay? So let's see. So this is minus 1. So this is minus 1 and 1, that's 0. Minus 1 and 5, that's 4. That's correct. The same thing goes here. So 2 and 4 get copied here. And here I get minus 4 plus 12, that's 8, right? So here we have this is called the upper triangular matrix. And this system can be easily solved by back substitution, right? That's exactly what we did before. All right? Any questions? It's easy, right? So the cool thing here is that the cool thing here are these elementary row operation matrices, right? Because essentially this was the input matrix. That's what we started with. That's what the input to our problem. And here are the elementary row operations I applied to convert it to upper triangle matrix by Gaussian elimination. So this matrix, notice that this matrix is upper triangular, and these matrices are a lower triangular. And the nice thing about matrix multiplication is that it's associative, right? Remember, we talked about, I don't think we proved it, but we certainly discussed about this property. It's definitely not difficult to prove. Associativity of matrix multiplication. Did we talk about it or not? I hope we did. Basically, it doesn't matter in what order do you carry out these matrix multiplication operations, right? The order we carried it in the derivation was that we first multiply by this, then by this, then by this. But the associativity with the matrix multiplication tells you that absolutely doesn't matter, that you can also multiply this, get some sort of matrix, I don't know, M or something, and then multiply the whole thing by this matrix. That's going to be the main idea of LU decomposition. We'll get there in a minute. So before we get there, let me elaborate a little bit on triangular matrices. Let me just give you the definition. I guess it's sort of obvious what is a triangular matrix, right? We have you talk about upper triangular matrices and lower triangular matrices. The upper ones, they have all entries below the diagonal 0. And the lower triangular matrices have all entries above the diagonal 0. That does not mean that there could not be some zeros. There could easily be 0 here or anywhere. A matrix with all zeros is both lower and upper triangular. That's totally fine. But what this means that there must be zeros below the diagonal and above the diagonal in this case. Okay? And the cool thing is that the matrices that we used for elimination, they were all lower triangular. If you think about it for a second, why are they all lower triangular, the matrices we use in Gaussian elimination? Who were paying attention, which maybe weren't because it was so simple. So what we are doing in Gaussian elimination, we're taking some equation, multiplying a row of a matrix, multiplying with something and adding it to another row, right? But there's also always a pattern to it. We're always taking a row above, multiplying with something and adding it to a row below, right? And that means that I guess you could probably, maybe let me show it here. You could probably notice a pattern to this, right? So this matrix, what it was doing was copying the first and third rows, and on the second row, what it did, it took the first row minus 2 and added it to the second row, right? So basically what this elementary, in full generality, if you observe the pattern here, but in general, the elementary row operation is an identity matrix, has ones on the diagonal, right? And has some scalar somewhere here, which says, is it same? this index I tells me which equation it takes, and it adds it to well, wherever it's here, to a row number j. And the point was that we are always taking a row above the one when we currently are, so this alpha is always below this diagonal of ones. Okay, that's why it's always lower triangle. Where was I? There. Okay, so the matrices we used in Gaussian elimination, they were all lower triangular. That's important. By the way, so why are the triangular systems important? Because we can solve them very easily using back substitution, right? Could everybody code it up in MATLAB? You don't really have to, but if you had to, for homework, for example. Oh, the homework will be more interesting than that. So yeah, that's the point of Gaussian elimination, to get it to the triangular form, which has an easy solution. Unfortunately, there is a catch. Remember, from the unmultiplication on the 1 by 1 case, there must be a catch, because there is a catch already in the 1 by 1 case. It would be weird if there wasn't a catch in the n by n case. So sometimes there is no unique solution, or sometimes there is no solution at all. Sometimes there can be an infinite number of solutions or no solutions. So in this case, if the last, so this is a perfectly triangular matrix, right? Everybody sees that? The catch is that here is 0 on the diagonal. So that's a problem, right? Because then I get an equation 0, z equals 0. Well, any z satisfies that. And it turns out that in this case, we have infinitely many solutions, right? Like, for example, you can verify that -7, 4, and 0 would be a solution. Let's try to verify it. Minus 14 plus 16. That's 2, right? And this would be 4. That's correct, right? But here is another solution. -4, 3, 1, I believe, is another perfectly valid solution, because the last row, that doesn't matter. It wouldn't even have to be there, right? Yeah, I could just take it out. I could just write it like this: 2, 4, -2, like a 2 by 3 matrix. That's an advanced case which we'll not really be talking about today. We'll talk about it later. But that's basically what it's equivalent to, right? That this guy wouldn't even have to be there. It's completely bogus. So let's see if this one satisfies. So this would be 3 plus 1 is 4. That's correct. And this would be -8 plus 12. That's 4, right? -2 is 2. So that's also correct. So there is another perfectly valid solution. And if you think about it long enough, that you find out that there is a pattern that you can actually add any multiple of 3 minus 1, 1, and you will still get a solution. We will I'll explain this better later when we will talk about null spaces and these advanced things. Let's concentrate on the simple square case for now. But my point here basically was that not every triangular system will have a unique solution. So in this case, we have an infinite number of solutions. That's an example. The problem is that that depends on the right-hand side. If the right-hand side is different, well, there's actually an interplay between the left-hand side and right-hand side. But for some combinations of matrices and right-hand sides, I can also have no solution, right? Look at this system. This system has no solution. Why is that? Because the second equation wants z to be 4, right? That's what the second equation says. X and y get 0, z gets 1, so that says z is 4. And the third equation says, what does it say? Well, z is 8, right? Well, there's no way to make both of them happy, so that's impossible. There is no solution. If I had, on the right-hand side, what do I have to? I would have here 16, then I would again get infinitely many solutions, right? So it sort of depends on the right-hand side. So let's postpone the discussion of these problematic matrices, and let's characterize how the good systems look like. So first of all, we will be today we'll be only looking at square matrices, and we'll be looking at matrices that are not singular. So what does that mean? That means that after you do the Gaussian elimination, it's actually one more trick. You need to do partial pivoting. I'll explain it in a second, because sometimes you have to reorder the rows. But if you can do that, if you can successfully apply Gaussian elimination and you get a triangular matrix such that all the diagonal elements are non-zero. Diagonal elements are called pivot elements. They are very important there. So if you have a triangular matrix, then these diagonal guys here, they are called the pivot elements, right? If I have upper triangle, then here can be something, can be some values. But here are zeros, guaranteed zeros, right? Like this, I guess. So that's a matrix. And these are called the pivot elements, the elements on the diagonal. So if all of them are non-zero, everything is cool. The back substitution works, no problem. You can always compute a unique solution. And the matrices that permit to be transformed by Gaussian elimination to this form, they are called invertible or non-singular. Okay, is it clear? Now the other case is that there are either one or more zeros on the diagonal. So one or more zero pivot elements. In this case, these matrices are called non-invertible or singular, and those are exactly the problem cases. In that case, the system will have either infinitely many or no solutions, and which case it is depends on the right-hand side. Remember the idea of the unmultiplication in the 1D case, 1 by 1 case, depended on the right-hand side. Okay? So for now, we will be talking about these good cases, about invertible matrices. Now here is some good news. The good news is that these elementary matrices we use in Gaussian elimination, matrices like this, they are all invertible. They are all non-singular. Why is that? Well, in that case, the inverse is actually super simple. It's like a rare case that the inverse would be that simple, because all you need to do is basically flip the sign of this off-diagonal element, and that's it. I think I talked about inverse last time, right? So you know how inverse is defined now. Inverse means that if I multiply the matrix with its inverse, I get the identity matrix. So amazingly, all I need to do here is flip the sign, and if I multiply it, I will get, so the first and the third rows in this case are copied no matter what, right? And here I'll get 2 minus 2, that's good. So I get 0 here and 1 here. So indeed I get identity. And most importantly, the inverse is also lower triangular. So that's beautiful. So you can see the algebraic properties like click together like a puzzle. So because the inverse is very simple and it's also lower triangular. So that will lead to one beautiful algorithm called LU decomposition. Before I get to LU decomposition, I will give you one nice property of triangular matrices that actually completes the picture of the beauty of the algebra. So it says that if I have two matrices that are both lower triangular, then their product is also lower triangular. So that's very nice. So I have a graphical proof for you, because after all, I'm a graphics guy. So here is a graphical proof. So we are talking about square matrices, n by n, right? So here is one matrix, and it's a lower triangle, so there are zeros here. Absolutely guaranteed zeros here. On the left from the diagonal, there can be zeros or non-zero. There's something, I don't really know what it is. Now, if I'm doing a product with another lower triangular matrix, it's the same structure, right? So again, zeros here, some maybe non-zeros from the left. And let's see. What we need to prove is that this will give us, again, a matrix of the same structure, right? So that what I need to prove is that here I will get zeros also. So that's what we are trying to establish. So all these elements have the property that the j index of the column is larger than the index of the row, right? If I take some element here, it has some index I and some index j, but the j will be more than I. And this guy, you know what? Let me take another one, so it's a little more obvious. Let me take one like here, or I guess better is here. So let's say the I is here and j is here. So what does it mean? Well, that means that I'm taking ith row from this matrix, right? And jth column from this matrix, okay? But here the non-zeros can be only here. Here the non-zeros can be here, right? So if I do the dot product, these non-zeros hit zeros here, and these non-zeros hit the zeros here. So the result will be 0, of course. Everybody got it? My graphical proof. If you wanted, you could like write like a formalish proof, but I think this is much more obvious. So it's basically obvious. If you multiply two lower triangle, two L matrices, you will get an L matrix too. The same property, of course, holds for upper triangular matrices. You could prove it in exactly the analogous way when we'll talk about transposition that will immediately follow from that. Okay, so now we put, that's the beauty of algebra. You can like build from simple observations, you can build some cool algorithms. That's, I guess, also the case of like the Rubik cube, that you can build some sort of rules how to solve things, and if you put them all together, it gives you a very elegant solution for the problem. So here is a very elegant way to solve linear systems. It's called LU decomposition. It's basically a way to put all this what we talked about together. So again, the idea is exactly the same. The idea is the Gaussian elimination. But here we have just a much nicer formalism for it. So what we are going to do, if A is an n by n matrix, you know that what was that word? We will need is it n by n? No, it's not n by n, because that would be a different n. Now, I mean, the matrix can be, let's call it m by m. What we will do, we will use some sequence of row eliminations, as many row eliminations as we need to get it to upper triangular form. And then we use the fact that, well, I guess the first fact we use is that the inverse of a lower triangle matrix is so simple. So if I multiply this from the left by Ln inverse, what I will get? I'll get Ln minus 1 to L2 L1A equals Ln inverse U. So I just multiply both sides from the left by Ln inverse, right? So I basically flip this Ln from here to over there. I can do the same one to Ln inverse, right? So basically get this guy out of here and put its inverse here instead. And if I do it for all of them, I will eventually get essentially a rewriting of the original matrix A in this form. So like a sequence of the inverses of the elementary row transformations from Gaussian elimination. That clear? And now I will use the property in the product of lower triangle. So first of all these are also lower triangle matrices. That's what we talked about just a couple slides ago. And the product of lower triangle matrices is also a lower triangle matrix. So that's awesome, because I just say, okay, these guys will be called now L, and this is a lower triangular matrix. So what I have done using Gaussian elimination, I essentially decomposed the matrix A into L and U, where L is a lower triangle, and U is an upper triangle. Okay, so if you want it graphically, looks like this. This lower triangle, upper triangle. So lower means that here are zeros. This means that there are zeros here. My A is this. Okay, let's take a look at our favorite example. Everybody got this? No questions? Oh, that's good. So let's take a look, how does it work in our favorite example. So here are basically also taking advantage of the matrix associativity, right? Because that doesn't matter in what order we multiply the matrices. So here are again, so this is our favorite system. Here are the elementary row transformation matrices, and here is the upper triangular matrix we got as a result. Okay. So I can do what I shown on this slide. So I can take work. So what I'm going to do, I'm going to take inverses of these matrices and put them in the opposite order here so I guess let's do it this way. So I take this matrix, I compute its inverse. Its inverse is simple. I just make this -1, 1 and put it here, right? So that's what you get here. Okay. Then I take this matrix, do its inverse, so that's -1, put it here. That's this one. Then I take this one, compute its inverse, and plug it in here, right? So that's exactly what was written here on this example. And now I can just multiply all these lower triangular matrices together, and I get just one lower triangle matrix. Product of lower triangles is a lower triangle, right, as I showed you graphically. So I have an LU decomposition of my input matrix, which was nothing like lower triangle, or didn't really have any special structure, right? So if somebody gives you LU decomposition of a matrix, like MATLAB, for example, it's already trivial to solve a system of matrix equations of the form AX equals B. Or another way, if you know the LU decomposition, solving systems like this is easy. Because if A is LU, you can do the following trick. Remember this trick, that this trick is very common in numerical linear algebra. So the trick is that you basically introduce a substitution. You introduce this helper or auxiliary variable y, and you first solve for Ly equals b. Okay. I'm assuming that all the matrices are well behaved, so the L has all pivots non-zero, so I can solve it no problem. Then I take the y, I compute it here, and I construct a new system where the y I plug on the right hand side, and now I solve for x such that ux is y. Again, I assume that all the pivots are non-zero, so I get a solution, no problem. And once I have done that, I realize that x is a solution of the original system, of course, because if I plug this y here, I get LU x equals b, but LU is nothing but a, so this x solves the original system. Everybody got it? This is called a factorization, sometimes a factorization of the matrix, and there are many other types of factorizations. There is for symmetric matrices or symmetric positive definite. Okay, we'll talk about these things later. There is a Cholesky factorization or LDLT factorization. There's many factorizations of matrices, many decompositions, and with most of them you can apply this type of trick or its simple modification. Now, why is this trick important is if you have to solve the same system with multiple right-hand sides. For example, would be a good example. Like I can think about examples in physics. If this system describes the linear elasticity of your system and the right-hand side describes external forces, then maybe you will have your object subjected to different external forces, right? At some time there will be some external forces. A little bit later, there will be completely new set of external forces. So the system A will be the same because the elastic object stays the same, but you'll keep getting new B's. So A stays the same, but somebody keeps telling you new B's and wants to solve the corresponding X's. No, make sense? So if you get the LU decomposition, that's actually great because once you have computed the LU decomposition, then given a new B, it's very, very easy to compute the solution. You don't have to be resolving the system all over again because you can reuse the factorization the decomposition into L and U. Okay, I guess I can do an example of how exactly this works. Let me just comment that LU decomposition was introduced by Alan Turing. So if some theorist will give you a hard time that you did not take class on Turing machines and that you don't pay enough respect to Alan Turing, then you go, oh, but we learned about LU decomposition. That was also introduced by Turing. So let me give you a numerical example of this very, very useful trick. I mean, we used it like in some algorithms in physics-based simulation, and it's really beautiful. Once you factorize the matrix, the problem of solving a system of linear equations, the complexity reduces dramatically. I'll talk about the complexity just in the next slide. Just bear with me a second. I'll just give you first an example and then talk about the complexity. So, our favorite system, you must be already sick of the system, probably. So the system you're already sick of has this LU decomposition. And if I give you a right-hand side to a 10, I think that's still the same as we did before. So the trick is to introduce this auxiliary variable y, and first solve for the y against our given right-hand side. I guess I'm not gonna do it to solve. I mean, you can solve that. It's just a back substitution. I'm not gonna bother you with doing it myself. And you get that the solution of this Ly system with this right-hand side is this. So the y is 2, 4, and 8. And then the second phase uses this as the right-hand side and solves for x, such that ux is this what was called y before. And once you solve, this is again easy, right? Because one is lower triangle, one is upper triangular. So in one case it's called back substitution, in the other case it's called forward substitution, but it doesn't really matter which way you go, right? In one way you go from here, so you compute the z, plug in here, compute the y, plug in here, compute the x. In the other case, you first compute the x, plug in here, compute the y, plug x and y here, and compute the z. Very simple, right? And the beauty is if someone then tells, oh, sorry, I meant the 2 was supposed to be 3, and the forces changed, so this is now -7. If you have the LU decomposition already computed and stored, it's very easy to just redo the 2 to forward and backward substitutions. So what do I mean by very easy, computationally easy? So first of all, what is the complexity of Gaussian elimination? Or equivalently, what is the complexity of LU decomposition? Well, what I have to do is, again, I guess I'll just do it graphically. It's sort of simple. So what I have to do is basically first take the first row and add its multiple to all the other rows, so I get zeros here, right? I basically use the scaled version of the first row to eliminate the first column except for the first element, right? Then I do the same thing again for the smaller matrix here, right? So, or you could say that this part has been already dealt with. There is something, there is zeros here. And I use the second, whatever remained from the second row anyway, to eliminate this piece here, right? So what this means, if this matrix is an n by n matrix, each of these operations takes O(n) squared, right? Because I have total number of n squared elements in the matrix. Each time I have to do a full sweep through the matrix. And another step, I also need to do a full sweep. It will be certainly a little bit less than n cubed, but there is, and I need n of these steps to bring it to this form, right? When there are zeros everywhere here. So altogether, I get O(n) cubed complexity. Does everybody understand the big O notation? Or is there somebody who doesn't know the big O notation? Okay, so the big O notation basically means, let me just explain it in this case. That means that that the number of flops for sufficiently high n is less than or equal than some constant times n cubed. That's what it means. So it's basically upper bound on the complexity. The complexity is, in this case, would be measured by elementary operations, by adds and multiples. And this means that the number for sufficiently high n, there is some constant c, exists a constant c, such that the number of operations is bounded by this function n cubed here. Okay, but it is this n cubed that should raise all sort of alarms for you, right? Because if n is 10, that means like 1,000 operations roughly, but how does it scale n cubed? Who has computer science background should be horrified by this. Because if you get a 1,000 by 1,000 matrix, or 10,000 by 10,000 matrix, or 100,000 matrix, that's pushing it really, right? And million by million matrix, that's probably not gonna happen, right? You probably wouldn't even be able to store a million by million matrix. This is actually the reason why the LU, by the factorization, like LU factorization, the Cholesky factorization, why they are so useful. Because what's the cost of back substitution? What's the cost of solving a triangular system of equations? So solving a general system of equations is n cubed, right? Solving a system of linear triangular system, what do you think? Think about it, I'll write it here. Who dares to guess the complexity? Well, I assume you can generalize yourself from the 3 by 3 case to any case, right? I said, so how does it work? You start here, you just compute the z directly, right? Then you take it, plug it in here, compute the y, right? Then you take these two values, plug them in here, and compute the last one. So what this is nothing but a sweep through the entire matrix, right? In a special order. If you then want to be careful about optimizations, you really have to worry about memory ordering and so on. We are not going to go to those details. I just want the asymptotic complexity. So if it's a sweep through entire matrix, that's O(n) squared, right? Obviously, n squared scales way better than n cubed, right? If you plotted the graph, then n cubed would go out of the window, n squared would also go, but like much slower, right? So that's why it's such a big deal. If you have pre-computed factorization, if you already have the LU, then you can solve the system in n squared time for new right-hand sides, as opposed to n cubed time, that's what it would take you for a completely new system. And the reduction of time from n cubed to n squared, that's huge, right? If you have 1,000 by 1,000 matrix, that means you saved yourself, you are 1,000 times more performant. That definitely makes a difference. Okay. Of course, this is really just the tip of the iceberg of solving linear systems. What typically happens in applications, actually we'll be talking in applications very soon on some typical linear systems you encounter in practical problems, and almost never you have to do it this way. Almost always there is some special structure to the matrix. Maybe the matrix is sparse, or maybe it's banded, or something like this. And in this case, you can hugely improve this time complexity. That's what's meant by intelligent linear algebra, as opposed to like this would be like, I guess, the brute force linear algebra. Like already using the LU decomposition trick that basically tells you how to bring it down from n cubed to n squared. If new right-hand sides keep coming, you still have to pay the n cubed cost once to actually do the factorization, right? The point is that if new b's keep coming, then you only have the n squared cost to do the back substitution. Okay. So what I would like to talk about next is all the things that can go wrong when solving linear systems. Even if the matrices, mathematically speaking, are invertible, that doesn't mean it's always going to succeed on a computer. And when solving practical problems, you need to be aware of that. That's what they usually wouldn't tell you, like in mathematical linear algebra courses, because that's like below them, some calculators which are imprecise. But in MATLAB, you have to deal with it. So you probably know that in a computer you don't really have any such thing as a real number. That real number is a mathematical abstraction that you can't really use in computations, right? What we can use in computations is an approximation, is basically a finite number of samples of real numbers. And one of the standard, there are two common standards, the single precision float and double precision double. So the float is 32-bit, and double, that's what this is about. That's a 64-bit one. Some GPUs I think also use half, which is like 16 bits, and there are certainly many variations. I guess some supercomputers probably would have 128-bit for higher precision and so on. But I think what MATLAB uses by default is the double precision, which has 64 bits. So if you look at it like visually, you have this real line, right, which has 0 somewhere. And all you got is some finite number of samples of real numbers that you actually can represent in the computer, right? And actually the sampling gets more and more sparse the further you go away from 0, and eventually you actually completely run out of numbers, right? There is some maximum number you can represent, or some minimal number you can represent. It's an exponential representation, so you can do pretty huge numbers. You can look up what is the maximum number you can represent, the minimum number you can represent. My point here is that the problem is rounding errors. And what I'm talking about is that rounding errors, if you do it naively solving linear systems, they can get you completely wrong result, even though the system is perfectly fine. It's invertible and it should have a right solution. You have to be careful about this. So you have to be careful about this because there is a thing called machine precision or machine epsilon, which is essentially the upper bound on the rounding error. So in float, it's something around 10 to minus 8. In double, it's something around 10 to minus 16, roughly. You can try, go to MATLAB and type 1 plus 1 e to minus 16. What do you think you will get? So 1 e minus 16, 10 to minus 16, that's some tiny, tiny, tiny number, right? What do you think you will get if you type this into MATLAB? 1, yeah. So this will be rounded down to 0. You will get just 1. This will be completely forgotten. That's the rounding error. There must be a rounding error because you only have 64 bits, right? If there was no rounding error in any real number, you could represent infinite information. Right? So let's talk about what the rounding error means for solving systems of linear equations, because that's what leads to the pivoting strategies I would like you to know about, because you'll have to implement them. So let me explain it on a simpler case. It's easier to sort of imagine a computer that only uses 3 digits of accuracy for each number. So here is actually how the rounding errors work. The problem is when you are adding some large numbers with some not so large numbers. So the representation works by having some bits for the exponent. So you always have some sort of, this is called, I think, the mantissa, and this is the exponent. But if you need to add the two numbers together, then you need to make the exponent the same on both sides, right? So if I'm adding these two numbers, then I have to make both exponents 10 to 3. And because I am only allowing myself 3 digits of accuracy, that means that this number, this will be completely rounded down. This will be rounded down to only 1.89. Okay? So in this case, again, we lose this completely. That's basically lost in the rounding error. Okay? So this is just a long way of saying that all arithmetic in the computer is approximate, which is fine, right? Because the errors are very small, right? So you would expect that the effect on the result when solving linear systems would be very small, right? The catch is that it doesn't have to be small. If you do it the wrong way, the error can actually be big. So here is an example of that. So consider this system of linear equations. So I have some very tiny number, 10 to minus 4, and I have a second equation. So if I'm looking at it roughly, so this is basically almost 0, right? And the solution is almost 1 and almost 1, right? So basically x is, if I round it, it'll blur my eyes or something. Makes sense, right? This is almost 0, so y is 1. Well, y is 1, that's fine. And 1 plus 1 is 2. Here it actually works exactly, right? So the solution is like almost 1 on x, almost 1 on y, with some little details. But let's take a look at what Gaussian elimination does in this case. If we just run it exactly the way I described it before, what do we get? Well, let's just try it. Let's just run it. So the algorithm says multiply the first equation by, eliminate the second one while multiplying this by 10 to 4 and adding it to the first one, okay? So if I multiply this by 10 to minus 4, 10 to 4, then this becomes minus x, so that's good, that eliminates it, that's what I wanted. And here I will get 10 to 4 plus 1 on y. And here I will get 10 to 4 times 1 plus 2, okay? So now the rounding kicks in, because I said we are only allowed 3 digits of accuracy, okay? So here I have 10,000 y plus 1, so that gets rounded to 10,000 and to 4. And here I have 10 to 4 plus 2, so it gets rounded down to 10 to 4. All right? No big deal. We just made a small rounding error, right? And let's see what happens. So here, the last equation, that just this plus 1 and plus 2 that disappeared in the process, and I ended up with 10 to 4y equals 10 to 4. So now I happily do back substitution, and I get that y is 1, right? Because 10 to 4 1 is 10 to 4. And if I plug it here, I get that 10 to minus 4x is 0, but that means that x is 0. So what I got is x0 and y0. And that's bad, right? Because remember, the original solution was something around 1 and 1, right? So, and here I got a horribly wrong answer, right? It's nothing, not even remotely close to the right solution. The right solution has x almost 1, here I got x0. So what is the problem? The problem is then we were dividing by the very small pivot element. We essentially amplified the rounding errors, which then created a large error on the solution. Okay. So could we? Yeah, that's basically. So the idea. Oh, actually, there would be even worse case would be. This could also be 0, right? The first equation could be y is 1, and the second would be x plus y is 2, right? In this way, I couldn't even run the Gaussian elimination, right? Because this one was just almost 0. If it's perfectly 0, there's no way I can use the first equation to eliminate the second one, right? So what do you suggest in this case to do? What would you do? So that we can still proceed with Gaussian elimination.
So do the row operation.
That's the key idea. Flip the rows. That solves this problem, and it turns out that this solves the numerical problem, at least this type of numerical problem as well. So in general, we can arrange things, and when we have more than 2 equations, we can pick the equation which has the largest magnitude pivot. By magnitude, I mean we look at the numbers in absolute value. So if I have my system in a matrix, I can just look at all these elements, take their absolute value, and look which one has the largest absolute value, which is the biggest guy in this column. And then I basically assume it's this one. Then I take this entire row, and I flip it with the first row. So here the first row will have a pivot with maximum magnitude. And that means that when I will be using it to eliminate all the other elements here in the first column to 0, I'll be only scaling it down. I will be only multiplying by a number between -1 and 1. Okay? And that's good, because the problem here essentially was that we had to multiply by a gigantic number. We had to multiply by 10 to 4, right? Which is why we got these small rounding errors, which got eventually amplified by the 10 to 4 and gave me completely wrong answer. So if you will be only scaling down, if you'll be only multiplying by something between -1 and 1, this is going to be cool. So yeah, just like you said, all we need to do is swap the two equations. And this is called partial pivoting. So let's take a look at it. Partial pivoting. So this is, I'm trying exactly what you suggested. So this was the system I had here before. Here, -10 to -4 plus y equals 1, x plus y equals 2. So now I just flip the two equations and try to apply Gaussian elimination here. So here I will be scaling down the first equation. So I will again have a rounding error here, right? I do 10 to -4 times the first equation plus the second equation. So the x gets eliminated. That always is the case. And here I have some tiny number here and tiny number here. So that again, I again have a rounding error. But here the thing is that the error here, well, this may be the wrong interpretation, that here this gets again rounded to 1. This gets also rounded to 1. So out of this equation, all is forgotten except for y equals 1. And back substitution is trivial. You can see the y here, and you get that x equals 1. And that's almost the right answer, right? The right answer was this. And if I get x and y as a solution, I'm pretty happy about that, right? If I got x 0.999 and y 0. Like this, I would also probably be pretty happy about that, right? That's close to the exact solution. So that's basically the best thing we can hope for in the presence of numerical error. Okay. So here is another type of problem that can happen. So this is called partial pivoting. This is the reordering of the columns. It solves most of the problems, but unfortunately not all of them. Here is another type of problem that can happen when solving systems using Gaussian elimination. So let's take a look at this example. Again, we are allowing ourselves only 3 digits worth of precision. So let's try applying Gaussian elimination to this system. So I have some large numbers here, but the pivot is pretty innocent, right? This already is after partial pivoting, if you want to look at it this way, because the magnitude of this element is larger than this one. So I'm scaling this down. And after the elimination, I get 10 to 4 plus 1, because I scale this one by dividing it by 10. And here I get 10 to 4 plus 2. So again, rounding kicks in and rounds this to 10 to 4, and this also to 10 to 4. So what I get is 10 to 4, y equals 10 to 4, which gives me that y is 1 and x is 0. And as you can see, that's again very far from the correct answer, because the correct answer should have x and y close to 1. Something around 1 for x, right? Here it doesn't even satisfy this, not even approximately, because we do 0 plus 1, we certainly don't get 2, right? So what's the problem here? The pivots are fine here, right? The pivots are not the problem. Problem is the problem is that the coefficients here, this first equation, there were some 10 to 5s. They are much larger. So what we could do is to basically just divide this entire equation by the 10 to 5. So basically the scaling is off. The scaling on the one equation is very different from scaling on the other equation. We can easily solve it by multiplying the same equation, the first equation by 10 to minus 5. After we do that, we get this system. This system we now subject to partial pivoting, which reorders it, and we get a nice solution. So that's row scaling. Now, in some cases, you want to do also column scaling. Column scaling, like typically, if your linear systems come from some applications, then the variables sometimes have some units, like volts or milliamperes or something. And sometimes it can happen that basically some of these units naturally have like larger numbers associated with them, and some of them have smaller numbers. And sometimes this can also create numerical problems due to rounding errors. So what you can do to combat this is scale the entire columns. What does it mean to be scaling columns? If you have your unknowns x1, x2, and so on to xn, you can basically introduce a substitution that you will say you'll be solving for x1. That will be, I don't know, 1,000 times the original x1. x2 prime will be 0.001 x2, and so on. So this corresponds to scaling columns. And this way you can again bring the system to be better behaved and reduce the rounding errors. Okay. Oh, by the way, another trick you can play here, and that's what leads to complete pivoting. You can also reorder the columns, because you could also do, I guess you could do like a third substitution where you could say that x1 double prime would be x2 prime and x2 double prime would be x1 prime, right? So what you can also do is switch the columns around. I wanted to explain more about the switching later, the permutation matrices, but I think it makes more sense to do that next time. So I think we will stop right there. Do you have any questions? Was it relatively easy? So the homework on this topic will come on Wednesday. I think now we are pretty much ready to do that. I have just 2 more details to clarify. Okay? Thank you.